So chapter 6, last thing I want to talk about is something called quantum numbers. Again, that was kind of mentioned in some of the rules I gave you before for the Pauli exclusion principle for filling up electron configurations. So 4 quantum numbers identify each electron uniquely. So I like to equate this to an address, okay? So if we have the address of the school here, 899 North Mill Street, Naperville, Illinois, we have bits of information there that narrows down exactly where the mail's supposed to go to. So we have the state, big, Naperville gets it smaller, then we have a street, North Mill Street, and then we have a specific number associated with it. So if we think of these as 4 distinct bits of information, think of it the same way with the electron. So the first bit of information we have about the electron is what we call the principal quantum number, and that's the little letter n, okay? And so we have 5, 6, 7, we have energy level 1 through 7 to identify where that electron is located. So again, that's a pretty big place for the electron to be other than the first energy level. So maybe that's the state of Illinois, okay? Then we have something called the angular momentum quantum number. It is going to be a cursive L. I don't like how they do L's in Word, by the way. This is determined by what we call the shape of the orbital. So if it is an s orbital, it's going to have a 0 for its L, or its angular momentum quantum number. It's a 1 for a P, a 2 for a D, a 3 for the F. So again, it's kind of like a coding system for where the electron is going to be located. So this is called the angular momentum quantum number. So this is where it gets a little bit more, needs a little bit more clarification. So number 3 is what we call the magnetic quantum number. It is a M with a subscript of an L. This depends upon what orbital it is. Is it a P, is it a D, is it an F? And this tells us what we call its orientation in space, its orientation in space. So I always like to describe this one using the P orbital, okay? So I have 3 P orbitals, a PX, a PY, and a PZ, okay? So I could say my L for P is a 1, okay? That is my angular momentum quantum number. Well, my ML, my magnetic quantum number, has to describe, is the electron here in the PX, is it in the PY, or is it in the PZ? So my ML for my orbitals is going to depend upon this 1. So maybe this is -1, this is 0, and that is 1. So what I have are 3 different MLs, magnetic quantum number, dependent upon how many slots do I have. So since I have 1, I could go plus or minus 1, and I could go 0. So it makes a little bit more sense if you also see a D orbital. So there are 5 slots for a D orbital, and my L is a 2. Okay, so my ML for these is going to be 0, and then you got -1, +1, and then you got a +2 and a -2. Okay, so you have 5 different places that you could put those electrons. So the ML just gives you some options of how to put that, okay? And then F is the same way. It is an L of 3, so you're gonna go anywhere from -3 to 3 for the F orbital. All right, now this will make a little bit more sense when we do an example, so just kind of bear with me, okay? And then finally, we have what we call the spin quantum number, called the MS. S is a subscript. MS could be one of 2 things. It could be a +1/2 or a -1/2. So what I want you to think about is the electron is spinning clockwise, or it's spinning counterclockwise. So like I said, in those rules, you could have to have opposite spins for the electron to exist in the same space. So this is telling you essentially that it's spinning in one direction or the other. All right, so this is how it kind of works. So let's look at zinc, for example. We have argon, and then we have 4s2, 3d10. Okay, those are the electrons, or the electron configuration of zinc. All right, so if I gave you a series of quantum numbers, could you tell me if they are applicable to the electrons here. I'm going to write down the following set of quantum number. All right, so I put N of 4, L of 0, ML of 0, and MS of 1/2. Is that legitimately an electron in this configuration? Well, 4 is telling me the energy level, so I have energy level 4. L is telling me it's an s orbital. That's here. ML is, of course, telling me I only have one location for the electron to exist, and then with the s orbital, I only have one location. And then it's spinning clockwise, let's say. Okay. This is an electron this is a set of quantum numbers to describe one of the electrons in the 4s of zinc. Is there another electron? Yeah. So you could have the same exact principal quantum number. You could have the same angular momentum quantum number. You could have the same magnetic quantum number, but this MS has to be different. So what it means to have 4 unique quantum numbers is we could have people living in Illinois, in Naperville, on Mill Street, but their house number is going to be different. So this is kind of their house number that kind of distinguishes them. So let's look at the 3D, okay? This is another set of quantum numbers. So I wrote down N is equal to 3, L is 2, ML is -3, and MS is 1/2. So another type of question I might ask is this a legitimate electron in the 3D? Well, yes, it's in the 3rd energy level, so that's correct. L is corresponding to 2, so that is the D, that is correct. ML is -3 though. Well, for L, I can only be -2 to 2, so -3 doesn't work. MS is 1/2 is perfectly fine. So this is what is wrong with the set of quantum numbers. So ML would have to be anywhere between -2 to 2 to be a correct answer. So again, this is a way to identify where the electrons are located because they can be in different energy levels, different SPD and F, and also spinning in different ways. So it's a way to identify. Okay, and then to finish up with this chapter, there's 2 terms that you're going to hear used to describe electron configurations, and we're going to hear this term again a little bit later on as well in our other chapters. The term is paramagnetic versus diamagnetic. If something is paramagnetic, it means the electrons are unpaired, and that means the electrons are attracted if it is in a magnetic field. If it is diamagnetic, everything is paired, it would not be attracted to a magnetic field. So how we're going to use these 2 sets of definitions is something like this. So if I look at sulfur, it is neon 3s2 3p4, okay? And what I'm going to ask is sulfur in the neutral state, okay, so this is not sulfur as an ion, this is just sulfur, not sulfide. Is this paramagnetic or is it diamagnetic? So what you have to look at is the p orbital, okay, has 4 electrons in it. So again, you can't just look at the fact that that's an even set of numbers, okay, because even might mean everything is paired up, okay? Unpaired would be something like a p3, all right? But when I fill a p orbital or a d orbital or f orbital, they fill one at a time and then they start to double up. So you really have 2 unpaired electrons here that could be attracted to a magnet, okay? So that means that sulfur is what we call paramagnetic. So what I'm going to use this is with electron configuration, and I'm going to ask you, is that substance paramagnetic or diamagnetic? And you understanding how the electrons are in that configuration should be able to answer that question.